Very good afternoon, students.
Good afternoon, sir.
Good
Good
afternoon,
afternoon,
sir.
sir.
Good
Good
afternoon.
afternoon, sir.
Good afternoon, sir.
Good afternoon,
So,
sir.
without wasting any time, we'll start with the discussion. Last class, we have seen different exceptional cases and we have seen how alloys are formed, what are the exceptions in electronic configurations, and all other things we have studied. Today, we are continuing with our discussion. So, the last class or the last discussion in the last class is formation of complex compounds. The D block elements has a tendency to form complexes. And what are the reason for the D block element to form complexes? It has small size. Yes, very good. It has small size, high charge density, and availability of vacant orbitals. We have discussed that in the 3D series or 4D series, the vacant orbitals are available. If the vacancy is there, then only the electrons can come. Ligands are those species which can donate their electrons. We will discuss this. Ligands will be discussed in complexes. What are different types of ligands are there? That we are going to discuss in the next chapter. Complex compounds. Yes or no? So ligands are those species which are electron donating. They are donating electrons. If I am donating money, means that doesn't mean you will take the money. Yes or no? If something is donating the electron, it doesn't mean the opponent will accept the electron. For the opponent to accept the electron, there should be some vacancy. There should be some vacant orbital. So ligands are donating the electrons, and the D block elements, they have the vacant orbitals, and that is why they are accepting those electrons from the ligands. They have high charge density, they have small size, and because of this they form complexes. If you look at the simple example, FeSO4 plus KCN, so we have Fe plus 2 ion and SO4. FeSO4 gives what type of ion, students? Fe plus 2, SO4 2 minus, and we have KCN, K plus and Cn minus. If Cn minus has to form a molecule with Fe plus 2, if you look at Fe is in plus 2 state. Cyanide ion has only minus 1 charge. To make the charge neutral, it should be forming FeCN taken twice. It should be forming a complex FeCN taken twice. This is not a complete complex. This FeCN taken twice again reacts with the excess KCN to form K4FeCN6. K4FeCN6 is a complex. It is a complex. You all know that this is a complex form. Reasons for this is the small size of D block element, high charge density, availability of vacant orbitals. Let us now try to understand the availability of vacant orbitals in Fe plus 2. Or what is the electronic configuration of Fe? 1s2, 2s2, 2p6, 3s2, 3p6, 18, 4s2, 3d6. Sorry, no, 26. Fe plus 2 means we have to remove 2 electrons. From where you will remove the 2 electrons? From the outermost orbital. So 4s2 only. So 1s2, 2s2, 2p6, 3s2, 3p6. After this, you have 3d6 and 4s0. In the 4s, you do not have any electron now. This is the electronic configuration of Fe plus 2 ion. D6 means how you will be having. In the D subshell, you have 5d orbitals. D6 electronic configuration means 1, 2, 3, 4, 5, and this is the sixth one, sixth electron. Yes or no? 1, 2, 3, 4, 5. After filling 5 electrons, then only I have started the pairing. This is your sixth electron. Now you may ask a question, sir, you are saying availability of vacant orbital since the since the starting of formation of complex compounds. But you look at Fe plus 2 ion. In the Fe plus 2 ion, every d orbital has got 1 electron each or not, at least. Yes or no? Then how come you say that Fe plus 2 has vacant orbital? And how come you say that it will accept electrons from cyanide? Cn minus is forming a new attraction with Fe plus 2 means Cn minus is the ligand, Fe plus 2 is the metal ion. Cyanide is donating the electron, Fe plus 2 is accepting the electron. But in Fe plus 2, do we have a vacant orbital? Look at that. Do we have a vacant orbital?
No, sir.
No, right? Obviously. So then how come the Cn minus is giving the electrons? Cn minus, whenever it is approaching, Cn minus cyanide ion, does it have negative charge or not? Yes. Cn minus is donating the electrons. Yes. Cyanide ion is donating the electron. What is the charge of electron? Negatively charged. It is donating the electrons to the Fe plus 2. But in Fe plus 2, we have all the d orbitals got at least one electron. Now imagine the situation. These are the d orbitals of iron. Cyanide is coming and donating. Because of the electrons from the cyanide, because of the approach of cyanide ion, the cyanide ion electrons will start repelling the electrons of d orbitals of Fe plus 2 or not? Yes or no? Whenever cyanide is coming and giving its electrons, the already present electrons in the 3D subshell of Fe plus 2, they will experience repel. They will experience a repulsion. Is that point clear, students?
Yes, sir.
I'm repeating again, listen carefully. We have a metal ion. Just listen carefully here. We have the metal ion. What is the metal ion? Mn plus. Here M is the Fe. So Fe plus 2 is your metal ion. Fe plus 2 is your metal ion. What is the complex I am talking about? K4 FeCN6. That means if you look at this complex, what you can understand? Cn minus is giving the electrons to Fe plus 2. What is the electronic configuration of Fe? Argon, like 1s2, 2s2, 2p6, 3s2, 3p6. 4s2 is there. Directly I am writing Fe plus 2 configuration. So 4s0, 3d6 means what? You have this configuration. After 4s, you have to fill electrons in 3d. After 3d, you have to fill electrons in 4p. You have to fill electrons in 4p. After 4p, you will fill electrons in 4d. Yes or no? Now, in the 3d, you have how many electrons? 6 electrons. How the filling has been done? Every d orbital has been given 1 electron, then the 6th electron got paid. Cn minus is coming. Cn minus is coming. How many cyanides are there in K4 FeCN6? In K4 FeCN6, how many cyanide ions are there?
6, sir.
6 cyanide ions are there. 6 Cn minus are present. Each Cn minus will give how many electrons? Each Cn minus, one cyanide ion will give how many electrons to Fe?
1 electron.
An electron.
Will provide 1 electron or 2 electrons?
1,
2
sir.
electrons. Every cyanide ion is giving 2 electrons to Fe, forming a coordinate bond. The Fe plus 2 will form a coordinate bond with the cyanide. What do you mean by coordinate bond?
That Cn will keep the electron, and by keeping it, it will share with iron.
Yeah, so 2 electrons are provided by cyanide only. So one bond is formed. That bond is formed by sharing of electrons between iron and cyanide only. That's good. But both the electrons are given by cyanide only. Fe plus 2 is now forming a coordinate bond with cyanide. Cyanide is the ligand. It is providing both the electrons for that coordinate bond. So understand this. We have 6 cyanide, 6 Cn minus are present. Each cyanide will provide 2 electrons. So 6 Cn minus will provide how many electrons? Each cyanide is providing 2 electrons. We have 6 cyanides. So how many electrons will be provided?
12.
12.
12. Very good. 12 electrons. In a atomic orbital, how many electrons can be occupied to a maximum in one atomic orbital?
2.
2 electrons. Yes or no? Atomic orbital can occupy a maximum of only 2 electrons. Also, every atomic orbital can occupy a maximum of 2 electrons. Listen carefully again. In K4FeCN6 complex, 6 cyanides are there. Each cyanide is giving 2 electrons because it is forming a coordinate bond with the metal. 6 cyanides are there. So 6 into 2, 12 electrons are going to be given or shared with iron and cyanide. Also, every atomic orbital can occupy a maximum of how many electrons? 2 electrons only. So how many atomic orbitals are required to occupy 12 electrons?
6.
6 obviously. So because one atomic orbital can occupy 2 electrons, we are getting 12 electrons from cyanides. So I require how many atomic orbitals? 6 atomic orbitals. So 6 atomic orbitals are required to occupy a maximum of 12 electrons. Everything clear, students, up to now? Everything clear or not? Simple maths only.
Yes, sir.
Yes or no? One cyanide is giving 2 electrons. We have 6 cyanides. So 6 into 2, 12 electrons are given in total. One atomic orbital can occupy 2 electrons only. So to occupy 12 electrons, we need 6 atomic orbitals. And I have written the electronic configuration of Fe plus 2. What is the electronic configuration of Fe plus 2? Argon 4s2, 3d6, that is for Fe. For Fe plus 2, argon 4s0. For Fe plus 2, we can say argon 4s0. After 4s, we have 3d, 3d6. 3d6 means follow Hunt's rule, 1, 2, 3, 4, 5, 6th electron paired. After 3d, what do we have? We have 4p, right? 4p. After 4p, you have
4D.
4d. Now, how many required, students? How many orbitals required? Just now I have told you. Because 6 atomic orbitals are required to occupy 12 electrons. So what are the 6 atomic orbitals you can expect? What are the 6 atomic orbitals you can expect? Can I say 4s has 1 atomic orbital? Yes or no? Because in Fe plus 2, 4s is empty or not?
Yes, sir.
Yes, sir.
In Fe plus 2, 4s is empty. That is 1 atomic orbital. In the 4p, how many atomic orbitals are there? 4p is the subshell. 4px, 4py, 4pz, 3 atomic orbitals. From 4s, I get 1 atomic orbital. From 4p, I get how many atomic orbitals? 1, 2, 3. 3 atomic orbitals. From 4d, how many required? Because I got 1 plus 3, 4 atomic orbitals are required. From 4d, I can have 2 more. Yes or no? So what are the possible atomic orbitals now? To occupy 12 electrons from 6 cyanides, what are the possible atomic orbitals? So cyanide can give electrons to 4s. Another cyanide can give electrons to 4p. Understanding this or not?
Yes, sir.
So 6 cyanides are there. 6 cyanides require 6 atomic orbitals, 6 empty atomic orbitals in the metal ion, that is Fe plus 2. Only then they can be donating their electrons. These are the electrons from the cyanide. This is one possibility. What is the one possibility? The cyanides can donate electrons to the 6 atomic orbitals of Fe plus 2. 6 atomic orbitals of Fe plus 2 which are vacant are 4s, 4p, 3 atomic orbitals from 4p, 2 atomic orbitals from 4d. Yes or no? 3 from 4p. Let me change the sign. Yes. So these are the electrons from cyanides. But other way what I am saying is the cyanide ion, whenever it is coming and it is donating its electrons, so this is your Fe plus 2, cyanide is coming and donating its electrons. Can the cyanide ion repel the inner electrons of Fe plus 2 or not? This is possible. One possibility is cyanide is giving electrons to 4s, 4px, 4py, 4pz and 2 atomic orbitals from 4d. So 12 electrons are done. Everything is fine. But the other possibility is cyanide, whenever it is coming and donating its electrons, will it repel the inner electrons from the 3D or not? Yes or no? Cyanide, whenever it is coming and donating its electrons, it will repel the inner 3D electrons also. Because of that repulsion, the 3D electrons can pair up. The 3D electrons can be paired up. This is nothing but your valence bond theory of complex compounds. Okay. So what can cyanide do is, we have this scenario, right? Yes or no? 6 electrons are like this in the 3D. What can be happening now is, in the 3D also we have 4 unpaired electrons. These unpaired electrons can be paired up. These unpaired electrons can be paired up. Why? Why they are pairing up? Because cyanide in the process of approach, it is experiencing repulsions with the inner 3D electrons. Now in the Fe plus 2, you have electronic configuration of argon 3d6. But how the electrons in 3d6 are there, or how the electrons in 3d subshell are there? Every d orbital get 1 electron and the other d electron and the other electron got paired. Because cyanide is approaching, because of repulsions from the cyanide ion, the pairing in the 3D happened. Because of that pairing, in the 3D itself we have 2 electrons or 2 d orbitals empty. This is your 3D, this is your 3D, this is 4s, 4px, 4py, 4pz. Understand now? So now what are the 6 empty atomic orbitals in Fe plus 2 in this new scenario? In this new scenario, what are the 6 empty atomic orbitals in Fe plus 2? 2 from the 3D subshell, 1 from the 4s, 3 from the 4p. In the earlier previous scenario, what are the empty atomic orbitals in Fe plus 2? 1 from 4s, 3 from 4p, 2 from 4d. So what is the hybridization in this first scenario? It will be sp3d2 because we are using 1s, 3p and 2d. What is the hybridization in the next scenario? 2d are used, 1s is used and 3p are used. d2sp3. What is the hybridization? d2sp3. d2sp3 means the inner d orbitals are used. sp3d2 means the outer d orbitals are used. Which is correct? This is the correct. This is the correct one. That means the cyanide is repelling the inner d electrons of metal ion. Because of that repulsions, the inner d electrons of the metal ion got paired up. Because of that, we got some empty atomic orbitals. Because of these empty atomic orbitals, they are available to accept electrons from the ligands. So D2sp3 is the correct hybridization of the complex K4 FeCN6. So you don't need to worry at all. We are going to discuss all these from the basics, again in the coordination compounds, but just I have given an idea. Understood now?
Yes, sir.
Okay, this is just an idea. You don't need to worry. So this is how the complex compounds can be formed, and this is how you can understand the hybridization of the complexes. And the reason for the d block elements to form complex is the availability of vacant d orbitals and a small size and high charge density. Right? Clear, students? Can I proceed with the catalytic properties or not?
Yes, sir.
Yes.
Yes, sir.
Okay, fine.
Yes, sir.
Very good. So similar to that, up to now we have discussed why d block elements form complexes, and if the complex is formed, what type of complex it is, what is the hybridization, all those things we can discuss. And the next properties of d block elements are catalytic properties. Write down this. The transition metals and their compounds are known for their catalytic activity. That means they can act as a catalyst. They have a tendency to act as a catalyst. Why? This is due to they can exist in multiple oxidation states and they can form complexes. The d block elements can form complexes. Write down these examples. D block elements can form complexes. Why? Just now I have told you why. Their vacant orbitals, we have looked at K4 FeCN6 also. The D block elements can form complexes and they have multiple oxidation states. They can be present in multiple oxidation states. Because of these two reasons, they can act as catalyst. Examples are important. Iron is used as a catalyst in Haber's process for the manufacture of ammonia. Vanadium pentoxide, it is used as a catalyst in the contact process for H2SO4 manufacture. Platinum for Ostwald process of nitric acid, preparation of nitric acid. Nickel, it is used in the hydrogenation of oils. Write down this, all of you. Examples are important. So why the D block elements can be using as catalyst? Can anyone say? Why the D block elements are acting as catalysts?
Variable oxidation state.
Yeah. It can form complexes. Very good, Dimple. And Shankar?
They exhibit multiple oxidation states.
Multiple oxidation states. Now the question starts. That is the same thing which we have on the slide, right? Now the question is, if a compound can form complexes, if a compound can show multiple oxidation states, then why that has to be acting as a catalyst? So if it show multiple oxidation states, what is the reason for that to act as a catalyst? So let it show multiple oxidation states. Let it form complexes. Are you understanding the question or not? The reasons what we have told to act as catalyst. The reason what I have told is D block elements are acting as catalysts as they have a tendency to show multiple oxidation states and as they have a tendency to form complexes. That's fine, well and good. Now the question is, if a D block element form complexes and if a D block element shows multiple oxidation states, what was the reason for that to act as a catalyst? So now we'll understand that reason in detail. Okay? So listen carefully. If you look at any metallic surface, here I am taking a D block metal. Can I say in the D block metal, like if I have this, I have a particular phone here. Imagine this as a metal. On the surface also I have atoms, because if I take an iron rod, on the surface also I'll have atoms. Inside the surface, that is inside the bulk, there also have atoms. Yes or no? It is not hollow, no. Iron rod, if you consider, if you keep any iron rod with you, is it a hollow rod? No. It has atoms throughout. It is not hollow. So that's what I'm saying. If you consider any metal, it is generally not hollow. It has atoms on the surface, inside the surface, like bulk. Everywhere it has atoms, like crystal. Consider the atom in the bulk. Like here, I am considering an atom inside the bulk. Students, always remember, one atom or one molecule will attract the other atom or other molecule by some intermolecular force of attraction. Anyone knew about these intermolecular forces? Or any types of intermolecular forces you know previously? You can just give your answers, right or wrong, that's completely fine. You are all learning, okay?
So dipole forces, metallic forces,
London forces.
van der
Very
Waals
good.
force.
Very good, all of you. You know a lot of things. So that's what I'm saying now. If you consider a metal like this phone, if you imagine as a metal, inside that metal you have some metal atom. On that metal atom, it is not a single metal atom present, right? Around that metal atom, you have similar metal atoms. Every metal atom is going to be attracting this particular metal atom. Since all the metal atoms are same, can I say all of them are attracting with the same force? Yes or no? Because metal atoms are same. So let us say that force be F. So this is F, 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 this is F. So if you consider any bulk atom means atom inside the metal, not on the surface. If you consider any bulk atom, that bulk atom is surrounded by same type of atoms in all the directions. All the same type of atoms are attracting with the same force. So what is the net force now, students? Net force on this bulk atom?
0.
Zero,
Obviously
sir.
zero, because it has equal force from all the side, from all the sides. If we are experiencing equal force, so the net force will be 0. Very good. So net force on the bulk atom, net force on the bulk atom is equals to 0. That is how bulk atoms are there. So that means any atom inside the bulk do not have any net force. It is not experiencing any net force. Consider now an atom on the surface. Here I will be considering this atom. And if it is the surface atom, above this surface, do we have any atoms of the same metal? Like this is the surface. This is the surface of the metal. Inside that surface, I have atoms. But above that surface, do I have atoms? No. It is all space. Yes or no? There is no atom. So only I have atoms. This is your metal. This is your metal. Inside the metal only I have atoms. So let us say I have an atom here. I can also have an atom here. I can also have an atom here. Since in the metal symmetry is there, I will also have another atom here. I will also have another atom here. I have just considered a few atoms, but you can say there are a lot of atoms inside the bulk. Now, since all the atoms are again same, can I say this atom is attracting the other atom with the force F? Obviously. This atom can also attract the surface atom with the force F. This exactly bottom atom that will also be attracting with the force F. This atom will also attract with the force F. This will also attract with the force F. Let us say this atom with respect to the surface is making an angle theta 1, and this atom is making an angle theta 2. Since the symmetry is there, we have another atom here which is making an angle theta 1. We have another atom here which is making an angle theta 2. Force is a vector or a scalar? force?
Vector.
Vector. So here I have a force vector, and it is at an angle of θ1 with respect to this particular line. So can I do the component? Can I take the component of this force in the x direction and y direction? Yes or no? Obviously. Can you say what is the component of this force vector in this x direction?
F cos θ1.
Very good. F cos θ1. I have symmetry, so I have another atom here which is at an angle of θ1. So what is the component of this force in the x direction? F cos θ1. Similarly, what is the component of this force in the y direction? F sin θ1. Similarly, the same force F at an angle θ1, that will also experience F sin θ1. What about the particle which is present at an angle θ2? That will experience force F cos θ2 in the x direction. Here also we have a particle at an angle θ2 that will experience force F cos θ2. What about the component of this force in the downward direction? F sin θ2. Yes or no, Farhan? What is the component of this force again in the downward direction? F sin θ2. So what happens to this F cos θ1 and F cos θ1? Will they get cancelled out or not?
Yes, sir.
Yes, obviously. What about F cos θ2, F cos θ2? They will also get cancelled out. What about this F sin θ1 plus F sin θ1? Can I write this as 2F sin θ1? Obviously.
Yes, sir.
F sin θ2 plus F sin θ2, I will write as 2F sin θ2. And I do have a particle exactly below that of surface particle. So it will have a force of F. So if you consider any surface particle, the surface particle will not have any horizontal force. If I have a surface particle, it will have no horizontal force because all those horizontal components are getting cancelled out. If you look at the surface particle, it is having some net downward force. What is the net downward force? F net on the surface particle. Can I call this as F plus 2F sin θ1 plus 2F sin θ2 plus 2F sin θ3, because at θ3 also I can have particle, plus 2F sin θ4 plus and so on. Yes. Lalit got the right
Yes,
answer. Now you know the net force on the surface is F plus 2F sin θ1 plus 2F sin θ2 plus 2F sin θ3 plus so on up to 2F sin θn. So we don't need to actually look at all these magnitudes, but what I can say instead is every surface particle has a net downward force. Every surface particle has a net downward force. How many surface particles are there? Can I say only one surface particle is there, or a lot of surface particles are there? Very high number, right? At every surface point I have a surface particle. So every surface particle has a net downward force. This means surface will have unbalanced forces, because the downward forces are there which are not balanced. Surface will have unbalanced forces. Because of these unbalanced forces, there will be some association of energy. Because on the surface, if you think of this as a metal, here on the surface I have metal atoms which have net downward force. Because of that net downward force, can this surface particle go into the bulk? Because of that force? Because of this net downward force, can the surface particle go inside the bulk? No. Why? Because if it goes, it experiences repulsions from the electrons. It has a net downward force, but it can't go. It can't go inside the bulk. That means every surface particle has a net downward force. Because of that, surface will be having unbalanced forces, which are responsible. These unbalanced forces are responsible for surface energy. What are they responsible for? For surface energy. Understand these, students, carefully. It is not some basic stuff. Very detailed explanation I'm giving. So if you have any doubts, you are free to ask. Every surface particle will have a net downward force. Because of this net downward force, surface will have unbalanced forces. Because of these unbalanced forces, surface will have some energy which is called as surface energy. Now imagine whenever that surface comes in contact with some chemical species like reactant molecules. In the reactant molecule, let us say, like bonding is there, AA bond is there. What is my reactant now? AA is my reactant. Let us say the reaction is AA plus BB converting into AB in the presence of some metal, D block metal. So what are your reactants in this reaction? AA plus BB gives rise to AB. AA, BB, these are reactants. What are your products? AB is the product. To balance, you can write 2AB. Okay. So what are your reactants now? AA and BB. Look at the surface. Look at the surface. Surface, everything is fine. But on the surface, we do have unbalanced forces or not? Yes. To balance these unbalanced forces, what will these AA molecules come? They will come and stick to the surface. AA molecules will come and they come and stick to the surface. What about BB molecules? BB molecules will also come and they also stick to the surface. Let me change the pen here. Yes or no? There is AA molecule, reactant molecule, which is coming and sticking to the surface. There is BB molecule, which is again coming and sticking to the surface. Why they are sticking to the surface? Anyone? Why they are sticking? Why AA and BB are coming and sticking to the surface?
Because unbalanced forces are present.
Very good. Because unbalanced forces are there on the surface. That's very good. True. Now, in the reaction, if I don't have any metal, reactants are AA and BB. They are converting into AB. In this reaction, can I say a bond present between AA that is broken? A bond present between BB that is broken or not? Yes or no?
Yes, sir.
Obviously, bonds are AA plus BB converting into AB means already present bond between AA that is broken. Already present bond between BB that is broken. Now imagine the situation. The molecule AA is coming and sticking to the surface. Imagine there are two friends, F1 and F2. F1 and F2, very close friends. They have very good bonding. Now the friend 3 comes. He started friendship with the second friend. There are two best friends, F1 and F2. Now the third friend comes into the scenario. He started new friendship with the friend 2. That means now F2 is developing new friendship with F3. So if F2 is developing new friendship with F3, what happens to the friendship of F2 with F1? It becomes slowly weakened or not? Yes or no?
Yes,
Are
sir.
you,
Yes,
are
sir.
you,
Yes,
are
sir.
you don't consider loyal friends and all that things? Okay, those are exceptional cases. Just imagine the interaction. If F1 and F2 has interaction, very good interaction, that's initial scenario. But if F2 is exposed to F3, the new interaction is developed between F2 and F3. So the old interaction has to be weakened. The same apply here. AA, the A and other A has a bond. AA bond is there. Now one of the A is developing interaction with the metal surface. Why? To balance the unbalanced forces. You only has given the answer. Because of this interaction, what happens to the AA interaction? That is weakened or not? Yes or no?
Yes, sir.
Yes, sir.
What happened to the BB
Yes,
interaction? That
sir.
is also weakened. Yes, very good. So AA interactions, BB interaction, that the bond between two A atoms, the bond between two B atoms, that is weakened now. That has been weakened. So if the bond is weaker, can it be easily broken? If the bond is weaker, it can be easily broken. If the
Yes, sir.
bond is easily, yeah, if the bond is easily broken, that means the reaction is happening at a greater rate or not. That means if the bonds are easily broken, the reaction is happening at a greater rate. Fastly the reaction occurs. So metal is actually catalyzing the reaction or not? Are you understanding this point?
Yes, sir.
So the bonds in the reactants, they were actually weakened because they means the reactant molecules come and stick to the surface. If the bonds are weakened, obviously that can be broken easily. Because of that, the reaction can happen at a greater rate. So reaction is catalyzed. Reaction is catalyzed. Write down that point, simple points. These unbalanced forces are responsible for surface energy. Now the reactant molecules will come and stick to the surface. Now the reactant molecules will come and stick to the surface, and because of this, the bond energy of reactant molecules is decreased, and thus reaction can happen at a greater rate. Reaction can occur at a greater rate. Greater rate means high speed. So reaction can happen fastly. So that is how the D block elements are catalyzing. And this is an example. Not only the metal, in the solution phase also they can catalyze. In the solution phase also they can catalyze. That means I can say the D block metal is forming a new bond with A. That means they are forming complexes. In that formation of complexes, their oxidation states can change. Their oxidation states can change. So what is the reason for this whole scenario? The D block elements provide their surface and they can form complexes with the reactants, and those reactants are converted to the products easily in a easier way. That is why they are catalyzing the reaction. All of you note it down, students. Note it down and let me know. These concepts will even overlap with your surface chemistry, adsorption phenomena. Done with the noting part?
Sir,
Yes, Nandana?
sir, when these reactants come and attach itself to the what do you say, ion atoms, so does that form a complex or they're just attracted through force?
That can be chemical bond formation. That can also be van der Waals force. That depends upon type of attraction seen.
Okay, sir.
Okay, it can be physisorption or it can be chemisorption. And we are taking just metal. But I have told you in the aqueous state also they can form complexes. Like Fe+3 ion, it is not a metal atom now. It is an aqueous solution. In that case, it can form complexes. Okay.
Yes, sir.
Okay, fine. Very good. Done. Okay, fine. So it is just an example. You can note down this example. Fe+3 is reacting with I minus to convert to I2 and Fe plus 2. Fe plus 3 to Fe plus 2 oxidation state change. Fe plus 2 is reacting with S2O8 2 minus to convert to Fe plus 3 and SO4 2 minus. So if you look at the whole scenario, Fe plus 3 is as it is. In the presence of Fe plus 3, I minus converted to I2, S2O8 2 minus converted to SO4 2 minus. This is a reaction which is catalyzed by Fe plus 3. The above given is an example. Where Fe plus 3 is used as a catalyst. Reason is simple. Catalyst can form multiple oxidation states like Fe plus 2, Fe plus 3, both are oxidation states. Catalyst can form multiple oxidation states, and they can form complexes. Yeah, Lalit has a very interesting question. Sir, catalyst can also decrease the rate of reaction. Then if they are forming the bonds and if the bonds are broken, how can you say the rate of the reaction is decreased? Can anyone say? So the decrease in the rate of the reaction can be assumed by increasing the activation energy. Lalit, you have to understand this by drawing the graph. Catalyst, what it is going to do is, we have a reactant molecules. Somewhere they will have energy. You have to look at thermodynamics only. So this is the energy you have taken on the y-axis. This is the energy of reactant molecules. Let us say they are forming some transition states and they are converting to some products. This is the scenario in the absence of catalyst. If a catalyst is forming a complex, and if that complex has lesser activation energy, it will be the positive catalyst. Like it is also in the presence of catalyst, EP. And if the catalyst is forming a complex which has a greater activation energy, then it will decrease the rate of the reaction. Now you can imagine like the scenario, like in a class 10 students are there and all of them, now I have kept a competition of high jump and I have kept the bar very low. Like you can imagine, I have just placed at 10 centimeter high. If the 10 centimeter high, if I have placed the bar, almost all the 10 students can pass through that. If I increase that to 1 meter, only 1 or 2 can pass. Are you understanding this or not? So in the absence of catalyst, the reactants has to cross this barrier, energy barrier, and then they reach the products. In the presence of catalyst, since the catalyst is forming a complex, if that complex has less energy, then more reactant molecules can pass, thereby increasing the rate of reaction. If that catalyst forms a complex which has greater energy, then less number of reactant molecules can cross the barrier. Yes or no? So catalyst can increase the rate of the reaction or it can decrease the rate of the reaction as well. Right? Good. You can understand that by writing this point. Catalyst increases the rate of reaction, by decreasing the activation energy, and it can decrease the rate of reaction. If activation energy is decreased, so more number of molecules can cross that barrier, and it can decrease the rate of reaction by increasing the activation energy, and there are some other catalysts known as auto catalysts. We will discuss that whenever at the right point of time. Auto catalysis. Note down all the students, note down and let me know when, then we'll proceed to the next concept. Why they hit done?
Yes, sir.
Yes. So after looking at the catalytic activities, after looking at the type of complexes formed, then we can go into the discussions of density. Density, what is the formula for density? Density is equals to mass by volume. So if you look at the 3D series, when you go from scandium to zinc, what is happening to the mass? Mass is increasing. What is happening to the volume? Volume can be referred from the radii calculations. If you look at radius of 3D series, how it is varying? From scandium to manganese, it is decreasing. After that, for iron, cobalt, nickel, it was almost same. After that, for copper and zinc, it is increasing. Yes or no? From scandium to manganese decrease, from iron to nickel same, from copper to zinc it is increasing. Density is equals to mass by volume. Mass is increasing. From if you are going from scandium to zinc, mass is increasing. And radius is also decreasing. Yes or no? Radius is decreasing for first to manganese. So mass is increasing, radius decreasing means volume decreasing. So volume decreasing means density should increase. So look at from scandium to nickel. What do you have? From scandium to almost nickel, there will be almost quite increase in the density because density is equal to mass by volume. Mass is increasing, volume is decreasing. But for the last elements like copper, since it is going to have higher radius, its volume has been high, so density should be low. So copper and zinc, if you compare, nickel copper will have maximum density, and then you have zinc. Okay, this order of density is a combined effect of increased atomic mass and varying atomic radii. And how atomic radius vary, why it is vary, we have seen that. Why? Because in the variation of atomic radii, we have two factors, nuclear charge and electronic repulsions. Based on that only, we have atomic radius in this fashion. So that is how you can understand the density in 3D series. If you look at 3D, 4D and 5D, the 5D series will have much higher density, then 4D and then 3D. Why? Because 3D to 4D, 4D to 5D, what happens to metallic bonding? Metallic bonding is increasing or decreasing?
Increasing.
Increasing. Metallic bonding increasing means all are having stronger attractions. If the attractions are stronger, the molecules or the metal kernels comes closer and closer. If the metal kernels are coming closer and closer, density will be increasing or decreasing?
Increasing.
Increasing. So that is why 3D less than 4D, 4D much less when compared to 5D. And these are the elements with the highest densities in the periodic table. Osmium 22.51 gram per centimeter cube, iridium 22.61 gram per centimeter cube. Write down these elements, remember. Elements with highest densities are osmium and iridium. 22.51 gram per centimeter cube. Iridium is 22.61 gram per centimeter cube. This can be understood. The 3D less than 4D, then much less than compared to 5D. This can be understood by increased metallic bonding. Right, students? That is the about the density of the that is about the density of your d block elements. And then comes to the oxidation states. We have already mentioned that d block elements show multiple oxidation states. But what was the reason for that? Reason is again the same point which we have discussed earlier. Small energy difference in the energies of Ns and N-1d subshells. D block elements will show variable oxidation states. Why? Because we have filling of Ns, N-1d, right? And the energy difference, if you look at, very small. That is why the Ns electrons can easily go to N-1d. Because of small energy difference, you can remove electrons from Ns as well as N-1d. D block elements show variable oxidation state due to small difference in the energies of Ns and N-1d subshells. Whereas if you go with the F block element shows variable oxidation state due to small difference in the energies of Ns, N-1d and N-2f. Because if you consider as in sixth period, we have what elements filled? 4f filled, 5d filled and 6s filled. 4f means 6 minus 2f. 5d means 6 minus 1d. 6s means 6s. You can say n minus 1, n minus 2f, n minus 1d ns. Yes or no? So the F block element shows variable oxidation states due to small energy difference in the energies of Ns, N-1d and N-2f subshells. And D block element shows variable oxidation states due to the small energy difference between Ns and N-1d subshells. Clear or not?
Yes, sir.
Yes.
Yes, sir.
Very good. The minimum oxidation state will be simply Ns electrons. How many Ns electrons are there? That will be the minimum oxidation state. Maximum oxidation state will be Ns electrons plus N-1d unpaired electrons. Look at the manganese. Manganese, what is the electronic configuration? Argon 3d5 4s2. Argon 3d5 4s2, write down. Argon 3d5 means you have each d orbital getting one electron. 4s2, 2 electrons in the 4s atomic orbital. So what is the minimum oxidation state of manganese? Manganese can show minimum oxidation state of
Seven.
minimum or maximum, Prachi? 7?
Maximum 7. Minimum 2.
Yeah, very good. Minimum oxidation state is equal to Ns electrons. How many Ns electrons are there? 4s2. So minimum oxidation state is equal to 2. And maximum oxidation state is Ns electrons plus number of unpaired electrons. How many? 1, 2, 3, 4, 5. And maximum oxidation state is 7. Right? That is how you can understand from the electronic configuration of manganese. Write down this table. Not writing like complete table. Write down which element has which is the most stable oxidation state for which element. The underlined elements are the most stable oxidation states. Underlined states are the most stable ones. Scandium, you look at the most common oxidation state. Most common oxidation state of D block or especially 3D series is plus 2. The most common oxidation state of D block elements, the most common and most stable generally, that is the plus 2 oxidation state, and the exception for this is scandium. Only scandium cannot show plus 2 states. Can you say reason why? Can you say why scandium will not show plus 2 oxidation state? Write the electronic configuration of scandium.
So because scandium plus 3 shows more symmetry and stability, so it does not require plus 2 state at all.
Very good. So argon 4s2 3d1, right? So if you remove 2 electrons from 4s2, you are getting scandium plus 2. But if you remove one more electron, you are getting the electronic configuration of argon, which is ultimately stable. So that is why scandium do not show plus 2. Chromium also do not show plus 1. Chromium do not show plus 1. You may get a confusion here. So why chromium do not show plus 1? Because if it, like chromium electronic configuration, if you write down, argon 4s1 3d5, right? So if you remove one electron, you are getting argon 3d5, which is half filled. But still that Cr plus 1 state that is not stabilized in the solution. You may again ask a question, sir, why? Because Cr plus 1, if it is undergoing, if chromium is undergoing a change to Cr plus 1, that Cr plus 1 has to be in the solution. In the solution, it can be coordinated with water molecules. Water can act as a ligand. So there is a formation of complex. And I am repeating this statement, listen carefully. The D block elements which have their electrons in the 3D subshell or 4D subshell or 5D subshell, and all these 5 d orbitals, they are not degenerates in the complexes. Can anyone say what is degenerates? Degeneracy means degeneracy.
Same energy.
Same energy.
Same energy. Although we are saying that D subshell have 5 d orbitals, the 5 d orbitals do not have same energy. There is going to be splitting of d orbitals. So that is why Cr plus 1 is not stable. So how the splitting of d orbitals will occur? That is a question. It can be happening upon the type of complex. Whether you have an octahedral complex or tetrahedral complex or square planar complex, based on that we will have different splittings. Okay. We will discuss that whenever time comes, like in the complex compounds. But chromium also do not show plus 1 states. Titanium plus 4, vanadium plus 3 plus 5, chromium plus 3 plus 6, manganese will show plus 2 plus 4 plus 6 and plus 7, iron plus 2, cobalt plus 2, nickel plus 2, copper plus 2, zinc plus 2. Copper in the aqueous solution, which is the most stable state? Copper, write the electronic configuration, argon 4s1 3d10, Cu plus argon 4s 0 3d10, Cu plus 2 argon 4s0 3d9. Which is the most stable oxidation state of copper? Cu plus or Cu plus 2? Look at the electronic configurations and say.
Cu plus.
So Farhan says Cu plus. Why Farhan? Why? Cu plus or Cu plus 2? Why it is stable? That's the reason. That's the question.
Sir, fully filled d orbital is
Stable. But
Yeah. In Cu plus, if you look at argon 4s0 3d10, we are getting this is completely filled d orbital. But if you look at this data, they have already mentioned copper is stable in the plus 2 state. That means argon 4s0 3d9. This is more stable. This is the most stable state. Copper is most stable in Cu plus 2. Why? Why? Because the Cu plus 2 electronic configuration is one factor. And the other factor is the Cu plus 2 is surrounded by H2O molecules, which is nothing, which is corresponding to hydration enthalpy. The hydration enthalpy also matters. So it has a greater hydration enthalpy. Cu plus 2 is more stable because of high hydration when compared to Cu plus. If you just look at the electronic configuration, you are getting Cu plus as a 3d10, so it should be more stable. But in reality, Cu plus 2 is more stable. Why is Cu plus 2 is more stable because of high hydration. You may ask a question, sir, how the hydration you can decide? Hydration enthalpy is directly proportional to charge density. Is directly proportional to charge density means what? Charge by volume. Density is nothing but mass by volume. Charge density is charge by volume. Hydration enthalpy is directly proportional to charge density. So it is directly proportional to charge, inversely proportional to volume. Look at Cu plus 1 and Cu plus 2, which has more charge? Plus 1 and plus 2. Cu plus 2. Yes or no? Charge is higher for Cu plus 2. So higher the charge, higher will be the hydration enthalpy. So Cu plus 2 is highly hydrated. Because of that, it is more stable. Understood, students? Clear or not? It is not
Yes,
just
sir.
the electronic configuration. Yes. Okay, let us proceed further then. Some stable oxidation states. Yeah, write down this, all of you, very, very important. Cr plus 3 is having T2G half filled. T2G, what is T2G? We'll study in complex compounds. T2G is the set of 3 d orbitals set of 3 d orbitals in octahedral complexes. So if you look at a Cr plus 3 ion that is having T2G, with T2G is half filled, that is why it is going to be stable. Mn plus 2 is stable. Manganese in the plus 2 state is stable because half filled d orbital. Scandium plus 3, Zn plus 2. These are the only one type of oxidation state is possible for scandium, that is plus 3. For zinc, it is plus 2. So only one type of oxidation state. As I have just told you, Cu plus 2 will have high hydration energy in aqueous medium. If you consider aqueous medium, it will have high hydration energy or high hydration enthalpy. And if you consider a solid state, it will have high lattice energy. Again, lattice energy is also directly proportional to Q1, Q2 by R. Yes or no? So more the charge, more will be the lattice energy. When compared to Cu plus 2 has more charge. So its lattice energy would be high. So Cu plus 2 will be more stable even in the aqueous medium as well as in the solid state. Reasons are high hydration enthalpy in aqueous medium, high lattice energy in the solid state. Look at Cu plus, Ag plus, Au plus, Zn plus 2, Cd plus 2, Hg plus 2. These all will have pseudo inert gas configuration. Pseudo inert gas configuration means what? What do you mean by pseudo inert gas configuration? Pseudo inert gas configuration means you have NS2, NP6, ND10. Yes or no? 18 electrons will be present in the outermost shell. In the outermost shell. If we have 8 electrons, then it is said to be inert gas configuration. Look at electronic configuration of Zn plus 2. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s0. Like Zn plus 2, write the electronic configuration. Zinc is argon. You don't write in terms of argon because we need 3s and 3p as well. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Zn plus 2, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. So you have ns2, np6, nd10, which has 18 electrons. So this is referring to pseudo inert gas configuration. Anyhow, any doubts? right? Scandium plus 3, titanium plus 4, vanadium plus 5, chromium plus 6, manganese plus 7, they will have inert gas configuration. They will directly have inert gas configuration like similar to argon. Is that clear, students?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, very good. Carbonyl complexes. Carbonyl complex means you can have complex like NiCO4, FeCO5. These are all carbonyl complexes. Whenever the D block element form a complex with the carbonyl, carbonyl means carbon monoxide, then you are going to have a zero oxidation stage. The D block element will be showing zero oxidation stage in the carbonyl complex. Plus 2, that is the most stable oxidation state in D block. Plus 3, most stable oxidation state in F block. Mn plus 7, that is the highest oxidation state in 3D series. Very important, all these facts are important. Important facts. In the 3D series, that means in the fourth period, you will have only manganese in the plus 7 state, which is the highest possible oxidation state. If you go with the other D block elements, like ruthenium and osmium, they can show the highest oxidation state of plus 8. Ruthenium and osmium, the highest possible oxidation state in the D block. Ru plus 8, OS plus 8, osmium plus 8 and ruthenium plus 8. Highest oxidation state in D block. In the 3D series, it is manganese. Most common and most stable oxidation state of D block is plus 2. Most stable and most common oxidation state of F block is plus 3. In the carbonyl complexes like FeCO5, NaCO4, carbonyl complexes, in those carbonyl complexes, D block element will have oxidation state of 0. The oxidation state of D block element in the carbonyl is 0, right? And if you go with the moving down the group in D block, stability of higher oxidation state increases. Like if you look at the group of chromium, molybdenum, tungsten, Cr plus 6, MO plus 6, W plus 6, out of all these three, which is more stable? Moving down the group in D block, stability of higher oxidation state increases. So which is more stable? W in the plus 6 state is more stable. Why? Why it is so? Why upon moving down the group, the stability of oxidation state increases? Why? Because they can easily lose the electrons. Because they are
Metallic
heavier.
character increases.
Yeah, very good. Because they are large in size, they can easily lose the electron. Metallic character is increasing. Yes or no? Because the heavier elements can easily lose the electrons. And highest oxidation state of an element, we are saying plus 7, plus 8. But where is this? In which compounds these are possible? Highest oxidation states of an element is stable with more electronegative elements like fluorine and oxygen. But oxygen is more favorable due to its multiple bond formation tendency. For example, if you look at MnO4 minus, how does it exist? Manganese will have double bond O, double bond O, double bond O, O minus. So manganese forms double bonds with oxygens. Because of that, stability is gained. In the Mn plus 7, in a MnF7, what is the oxidation state of manganese? Calculate the oxidation state of manganese in MnF7.
Plus 7.
Plus 7.
Plus 7, 1 manganese, 1 into X, 7 fluorines, 7 into minus 1, that should be equal to 0. So manganese X should be is equal to plus 7. But MnF7 do not exist. Does not exist. Why? Why? Because there are only single bonds throughout. The fluorine cannot involve in the double bond formation. oxygen is more favorable to form or to have manganese in the highest oxidation stage because of its double bond formation. Xenon also forms XeOF4, XeO4, XeO2F2. Only with the fluorine and oxygen, the highest oxidation states are possible. When you compare fluorine and oxygen, oxygen is even more favorable because of its multiple bond formation tendency. Yes or no? Highest oxidation state of element is stable with more electronegative elements like fluorine and oxygen, but oxygen is more favorable due to multiple bond formation tendency. Is that clear, students?
Yes, sir.
Yes, sir.
Yes, very
Yes,
good.
sir.
Then the last point which you are going to study is electrode potentials. Electrode potentials or electrode potential. What do you mean by electrode potential? Can anyone define? Right or wrong? You don't need to worry at all. Just try to answer. Electrode potential. What is it? Because we want to study it, no? So we should know at least the definition, then only we can analyze it. Prachi, sure? Just let me know if you're done. Can anyone say electrode potential? What is it? So Dimple says difference between cathode and anode potential. Okay, fine. Simple statement, students. When a metal rod, yeah, someone is saying.
The different factors that determine the stability
Okay,
of the oxidation states.
okay. So what is that potential? How it is developed means, listen carefully. When you place a metal rod, when I place a metal rod in a solution of its ions, the metal rod, like if I place a zinc rod in ZnSO4 or copper rod in CuSO4, the metal rod has a tendency to undergo oxidation. That means the metal ions from the metal rod can come into the solution, or the electrons from the solution, they can go and accumulate on the metal surface. That means oxidation can happen or reduction can happen. If the metal rod, like let us say we have Mn plus, Mn plus, Mn plus, Mn plus. Let us say with an example also with the Zn plus 2. In the metal I have Zn plus 2, Zn plus 2, Zn plus 2, Zn plus 2. I have considered a very small part of the metal where 4 Zn plus 2 are there. Every Zn plus 2 obtained means every zinc is giving out 2 electrons also, 2 electrons, 2 electrons, 2 electrons, 2 electrons. Let us say 2 Zn plus 2 come into a solution. Now what happens? Now what happens? Here we have a solution. When 2 Zn plus 2 comes into solution, we have only 2 Zn plus 2 now. Zn plus 2, Zn plus 2. Earlier, how many electrons are there? With every Zn plus 2, we have 2 electrons. So 2, 2, 2, 2, 8 electrons are there. Now also 8 electrons will be there. But how many Zn plus 2 are there? Zn plus 2 is only 2. Because of the Zn plus 2 coming into a solution, what solution is it? It is ZnSO4 solution. That means extra Zn plus 2 is now present in the solution. And we have extra electrons in the metal. When a metal rod is placed in a solution of its ions, the metal can have a tendency to undergo oxidation. If it undergoes oxidation, we have extra negative charge on the metal rod and positive charges accumulate around the metal rod. Two charges separated by some distance, they provide the potential. Because of its electrical double layer formation, some potential has been developed. That is nothing but electrode potential. In simple words saying, when a rod is dipped in a solution of its ion, there is some electrical double layer formed. Because of this, some potential is developed. That potential is nothing but electrode potential. That potential is nothing but electrode potential. Right now, there is no regular trend in these values. The electrode potential values, there is no regular trend. And if you try to plot the graph, you are getting graph like this. You are getting a graph like this. The calculated values and the observed values. Difference is there. This why there is no regular trend means there is irregular variation of ionization energies. That is ionization energy 1, ionization energy 2. If you calculate this, there is no regular trend in the ionization energies of d block elements. Because of exchange energies in the ionization energies, if you remove one electron, the formed electronic configuration may have a difference in exchange energy. That is why ionization energies do not have regular trend. Write down this point. Ionization energies generally from left to right, ionization energy should increase. Ionization energies do not have regular trend, because of very low energy difference, between Ns and n-1d subshells. Also, whatever the electronic configurations we are obtaining, there will be difference in the exchange energies. Also, there is a difference in exchange energies. Because of these two reasons, there is no regular trend for ionization energy. So if you are talking about electrode potential, what I am talking about, from the metal lattice, I have to get a metal atom. That metal atom has to undergo removal of one electron, then second electron, then we get a metal ion that has to be undergoing the hydration. Yes or no? How many points are involved means, listen carefully. I have a metal rod. Like we'll give the analysis in the next slide. Listen carefully here. I have a metal rod. From the metal rod, I am getting metal atom. I am taking that metal atom to the gaseous stage. Gaseous metal atom. I am removing one electron. Minus electron. So I am getting M plus in the gaseous form. Removing one more electron, I am getting M plus 2 in the gaseous form. This is in the aqueous media. So M plus 2 aqueous. So what are the energy changes involved here? Look carefully. I have a metal rod. Yes or no? I am talking about ionization energies. I am talking about sublimations. If I am eager to discuss about electrode potentials, what are the energies affecting electrode potential? I have to look at. What are the energies affecting electrode potential? From the metal rod, from the iron rod, I have to remove one iron atom. What is this energy called as? From the metal rod, removing one electron, remove one atom. What is this energy called as? From the metal rod, if I want. Yeah, very good. Enthalpy of atomization, delta HA. Enthalpy of atomization. From the metal atom, if I want to convert in the gaseous state, what is that? Enthalpy of sublimation. Very good. From the gaseous metal atom, one electron removed. So what is this? Ionization energy 1. From the unipositive metal ion, one more electron removed. Ionization energy 2. From that dipositive metal ion in the gaseous state, whenever it is added to water, it will be hydrated. It will be hydrated, no, in the water molecule. So delta H of hydration. Therefore, electrode potential depends upon how many energies? Depends upon delta H of atomization plus delta H of sublimation plus ionization energy 1 plus ionization energy 2 plus delta H of hydration. So upon all these values, the electrode potential is depending upon. And if you look carefully, you have exceptions in atomization. Enthalpy of atomization has some exceptions. Ionization energies 1 and 2, they have exceptions. Why? Just now in the previous slide, I have told you, ionization energy do not have regular trend because of very low energy difference between Ns and N-1 subshells. And there's also a difference in exchange energies. So ionization energies has exceptions. Sublimation has exceptions. Atomization has exceptions. Hydration is also has exceptions. So ultimately, electrode potential will not be having a regular trend. Understood now? Why the electrode potential will not have regular trend? Because it is depending upon all these facts. Because metal is converting into metal ion, no? In the electrode potential. The potential difference developed between a metal rod and its ions in the formation of electrical double layer. That is nothing but your electrode potential. So that is depending upon all these energies. So obviously what you can say, it is not going to have a regular trend. But from thermodynamics, I can say delta G naught is equals to minus NF E naught. Electrode potential, if it is positive, what happened to delta G? N is number of electron change positive. F is Faraday positive. Electrode potential, if it is positive, delta G naught would be negative. Delta G naught is change in the Gibbs free energy. If delta G naught is negative, what happened to the reaction? It is spontaneous. If E naught, electrode potential, is negative, delta G naught will be positive. If delta G naught is positive, change in Gibbs energy positive means non-spontaneous. So which metal will act as a better oxidizing agent depend upon its structure or not. Because electrode potentials gives information regarding whether it will act as oxidizing agent or reducing agent. Electrode potentials are obtained from enthalpy of atomizations. Enthalpy of atomization is the amount of energy to remove an atom from the metal crystal lattice. So everything depends on the structure. If the structure of the metal crystal is very strong, enthalpy of atomization is very high, which will be affecting electrode potential, which ultimately affects spontaneity. So that is how our chemistry is related. Whether a particular metal atom is acting as a good, strong reducing agent or strong oxidizing agent, that again depends upon the crystal lattice structure of that particular metal. And also hydration enthalpies, ionization energies, sublimation energies. Understood these points or not?
Yes, sir.
Okay.
Yes.
So what ultimately we can say, we are discussing a lot of points. What ultimately we can say is electrode potentials do not have regular values because of these reasons. Delta G naught negative means spontaneous. Delta G naught positive means non-spontaneous. Fine, students, these are the most important points of D block elements. Different characteristics of D block elements. In the next class, we will be looking at different compounds of D block elements like K2Cr2O7, KMnO4. And then probably we can start with F block. Once we are done with the D block and F block, we can start with our complex compounds. Hope you all are understanding these sessions. If you have any doubts, you are free to ask. Thank you all. Bye-bye.
Thank you, sir.
Thank you, sir. Thank you, sir. Thank you, sir.
Thank you, sir.